Hello, my name is Laz. I have been in the fabrication business for quite a while, running my own small shop. My background is in transportation industry engineering, which covers building all types of vehicles from the ground up. But that is not the business I am in today. We manufacture architectural design building elements, though that is not really relevant right now. I purchased the IPG Photonics Lightweld 1500 laser welder as soon as it was released in the United States. I believe the release was around late 2020, and I got mine in early 2021. When it welds, the speed and quality are outstanding, unmatched compared to conventional welding procedures. But I am here to talk about the cons, not the pros. On YouTube, everyone seems to highlight the positives, but not many people want to discuss the downsides. I am not bashing the IPG Lightweld 1500. I am talking about the general cons of laser welding, and along with that, the darker side of the Lightweld 1500 itself. In the first part, I'm going to talking about the physics and principles of the laser welding. Later, I will explain why did I modified my laser welding gun, lockout wiring, and how did I do that. With that, I got rid of an extra tangling wire on the shop floor, eliminated a notorious failure point of IPG laser welding gun, and made some procedures quicker and easier, and made my system unsafe. Memo, not advised. If you don't understand the fundamental physics of laser welding, how the beam interacts with the metal, then stick around and watch this video to the end. By the time you're done, you'll have the laser degree you've always dreamed of. Laser welding is precise science, not guesswork. The savages of laser welding. Laser welding isn't magic, it's physics. The beam excites electrons, heat builds, metal melts, plasma forms. If you don't get that, fine, but don't pretend you do.
I know what I'm
Stop
doing.
making dumbass videos. In a conversation, you can ask stupid questions and get corrected, but when you put out a dog shit video, it sticks, and your followers end up thinking that's the truth. Clarifying the science, laser power, wattage, doesn't directly mean beam temperature. A laser beam is light, not heat. It doesn't have a temperature in the usual sense. Wattage refers to how much energy per second the laser delivers. Heat creation happens when the metal absorbs that energy. More wattage, more energy delivered equals to more absorbed energy by the affected material, faster heating, deeper melt. Heat affected zone, for short, HAZ. Because the laser is so precise, the region where electrons get excited and thus heat spreads is very narrow compared to traditional welding. That's why laser welding is prized. Minimal distortion, clean seams, and controlled melting. Clear explanation. The laser beam delivers energy in the form of photons, not heat. When those photons are absorbed by the metal's electrons, the electrons get excited. The excited electrons transfer their energy to the atomic lattice, causing vibrations. Those vibrations are what we perceive as heat. As the temperature rises, the metal melts, and at very high intensities, melting leads to plasma formation. Beginner-friendly phrasing. The laser doesn't bring heat with it. Instead, the light energy shakes up the metal's electrons, and that vibration creates heat inside the metal. The heat then melts the surface, and if the energy is strong enough, the metal melts into plasma. Light, including laser beams, travels in straight lines through a uniform medium. When it encounters a new medium, its behavior changes. Two laws govern this change: reflection and refraction. A laser beam follows the law of reflection. The angle of incidence equals the angle of reflection. If the surface were a perfect mirror, the beam would bounce back cleanly at that angle. But real metal surfaces are not mirrors. They have grain, oxidation, scratches, and texture. That causes the reflected rays to scatter like a spray pattern. Micro-reflections shoot off in multiple directions, some sideways, some upward, some absorbed into the grain. The law of reflection states that the angle of incidence equals the angle of reflection. On a mirror-smooth surface, this bounce is clean and predictable. In welding, reflection defines your safety corridor. If the beam only reflects, there is no melting and no weld bead. Back reflections can damage optics and injure operators. Scattered rays are not harmless. They can arc sideways, upward, or back toward optics and people. Always position yourself behind the beam path, outside the reflection cone. Wear laser safety eyewear matched to your wavelength and optical density. Cover exposed skin and avoid placing hands or forearms in reflection paths. If a reflection can burn a lens, it can injure eyes and skin. For safety, place non-flammable shielding around the welding or laser cutting area, with an underlayer beneath whenever possible. This material should absorb both direct and reflected laser beams, eliminating hazardous reflections. Ideally, the entire operation should be conducted inside a dedicated safety booth enclosure designed specifically for laser welding. Such enclosures provide controlled boundaries, prevent stray reflections from escaping, and, in larger operations, are essential to stop workers from inadvertently entering the affected area. In laser welding, a large weld gap, often called a fit-up issue, creates a fundamental conflict between the precision of the laser and the volume of material required to make a joint. Because the focused laser spot is incredibly small, 25 to 60 micron, it cannot bridge gaps the way other welding procedures can. The most immediate physical problem is that the laser beam simply passes through the gap without touching the material. And as I explained before how the laser beam behaves, the side-to-side wobble hits the edges of the material in a shallow angle, therefore bounces off of edges and will not create plasma. Using a square pattern, the laser beam will travel parallel to the material edges and creates the plasma, which can be directed into the small weld gap by the gravity only and/or with the inert gas. If you do not own a precision cutting machine, you will have lots of problems with the fit-up, and if you have, that's fine attitude. The joint gaps should generally not exceed 10% of the material thickness, or approximately 0.1 millimeter, 0.2 millimeter maximum. If you running wire feeder, you can get away with a larger gap, but the gap should not exceed the wire diameter. Memo: Interlock wiring modification. IPG laser welder gun. I modified the interlock wiring in my IPG laser welder gun, and here is how I did it. There is a green wire routed to the pogo switch that connects into a yellow wire. Note: on some other IPG guns, this wire may be a different color. For example, on my other gun, it is blue. I created a three-way connection using 18-gauge wire and routed it back into the lower part of the gun where the 3D printed plastic cover is located. I soldered a microswitch onto the new wire with the other end connected to the interlock wire. Then I drilled an 8mm hole in the plastic cover and installed the microswitch inside. Now I can cycle the switch between NO and NC. I chose not to cut the orange wire because it would be more cumbersome. The orange interlock wire comes directly from the machine, and cutting it requires stripping away protective shielding, which degrades the integrity of the wiring. Running a short 18-gauge wire back from an existing connection is easier and safer. Memo: Interlock wiring clarification. IPG laser welder gun. I need to clarify a few things, since the wiring may be confusing. The interlock wire coming from the unit itself is orange, and on my machine, the free-running interlock wire with the clip is also orange. My microswitch connects this wire to wire 1, and the installed wire runs back to the pogo switch connection. As I mentioned earlier, I chose to connect at the pogo wire so I would not have to disturb the original wiring. With this modification, the gun is technically in an unsafe condition, but it eliminates the usual failure point at the pogo connector. The advantage is that I can now float the gun. I do not have to touch the material in order to perform certain tasks. Memo: Microswitch startup state. Error code 025. Before powering on the machine, the microswitch should be set to the normally open state. The reason is that when the unit boots up, it starts in its normal idle condition, not welding yet. If the switch is set to normally close during startup, the unit will immediately throw error code 025. In that case, you must cycle the switch, press the lower trigger once to clear the error, then return the switch back to NC. IPG 1500 Lightweld. Ergonomic and Design Failures 1. Ergonomics and Trigger Logic. The gun body demands a full hand grip, thumb and all fingers wrapped, just to engage two oversized buttons. Once released, the gun becomes unsupported, compromising stability and control. The dual-button design is redundant and counterproductive. A single well-placed trigger would suffice. The internal safety lockout pogo connector is prone to melting under longer continuous use. If you run a very long weld bead, the gun tube will heat up just enough to melt the pogo connector plastic body, dislocating the pin itself. Once compromised, even minor play in the bayonet lock causes intermittent loss of connectivity. This is a critical design flaw in both thermal tolerance and mechanical resilience. Cable management. Pre-industrial cable protection is chaotic. The wire loom tubing sleeve is cut in half and wrapped instead of pulled over the cables and the fiber optics. And it was wrapped here and there with Velcro strips, which is catching everything you intend to pull over your line. Zero strain relief, zero routing logic. The oversized wire connector snags on workpieces or on the welding table itself constantly. Cable wrap is subpar, more decorative than functional. An additional cable on the shop floor is a trip hazard. Once, I tripped in the wire, dragged the gun off the table, and the gun fell to the ground. The galvo stopped functioning after the accident, and the entire unit had to be sent back for repairs. Gas connector, sag-induced leaks. The push-in gas fitting protrudes excessively and uses soft tubing, causing sagging and unintended loss of inert gas. Without reinforcement, sagging leads to gas loss and inconsistent flow. A built-in 8 to 10 mm quick connect would resolve both footprint and reliability. With that, I pretty much covered the flaws of the IPG 1500 Lightweld system. It did have lots of other issues, but the manufacturer fixed those over the years. I still feel like I was application tester for IPG, and I had to pay for it instead of getting paid for it. At the same time, I have emphasized the customer support is outstanding, but the design engineers do not listen to user input, and still today, the unit's showing the same symptoms as the early units. No design changes to make it better. Chinese laser welder versus IPG 1500 Lightweld. The IPG 1500 Lightweld not comparable in any way, compared to what the overseas unit offering. IPG side-to-side wobble versus dual axis wobble on the galvo allows pre-programmed geometry, not only left and right wobble, but circles, triangles, and more. 25 micron beam, lighter gun weight, single button operation, and a touchscreen interface with clear options. Cable management is fluid, disconnectable at the unit itself for transport. 3-in-1 system, weld, cut, and clean at a fraction of the price, with 50% more penetration at the same power level. Chinese manufacturers also provide warranty support. When my Chinese laser unit had an issue, I did not see any negative impact compared to the United States unit. I received the replacement part within 10 days and was able to install it myself. By contrast, when the Lightweld needed repair, I had to ship it back to the manufacturer. The turnaround was much longer, about 20 days of downtime compared to the overseas unit. Fiber optic cable, serviceability. The laser source fiber optic cable should be disconnectable to allow quick and easy field repairs. Like what you will find on the most overseas unit, you disconnected the fiber optics on the welding gun and the laser source in shop conditions. The cable harness also disconnect at the gun and the unit. No large connector in mid-run. Ideally, the source could be removed, the cable disconnected, replaced, and reassembled. In my case, the fiber optic degraded after about 8 months, and the entire unit had to be replaced since service was only possible at the factory repair shop. Trigger design, ergonomic flaw. The trigger design is flawed. For users with smaller hands, the gun body is too large to hold securely unless the lower button is pressed. Even with larger hands, the same issue applies. This design can also trigger error code 028 if the upper button is accidentally engaged. Improved weld quality. By distributing laser energy in controlled geometric paths, dual-axis guns does not reduce heat concentration and minimize distortion, but it does produces stronger joints, greater fatigue resistance, and smoother weld seams. Deeper penetration and thin sheet capability. Dual-axis control enables both deep penetration welds and precise thin sheet welding down to 0.01 millimeters without damaging surrounding material. This makes them suitable for applications ranging from automotive frames to delicate electronics. Larger stationary units can achieve penetration up to 20 millimeters in a single pass, depending on laser power. Portable high wattage units typically reach about 12 millimeters, close to 0.5 inches, when operating in the 25 micron range. Shielding gases. For most laser welding applications, you can get away with using nitrogen alone as the shielding gas. It is inert enough to protect the weld pool and prevent oxidation in typical shop conditions. Where things change is in specialized industries like aerospace. If a specification sheet or welding procedure specification for short WPS calls for a particular gas mix, argon, helium, or combinations, you must follow that requirement exactly. Those standards exist to guarantee mechanical properties, corrosion resistance, and certification compliance. The real point is, do not skip shielding gas entirely, as many demo videos mistakenly do. But also, do not assume you always need exotic mixes. Nitrogen is sufficient for most general laser welds unless the WPS dictates otherwise. Geometric dual-axis wobble increases total heat input compared to side-to-side motion. It does not reduce heat concentration or distortion by default. The advantage is wider beads and stronger fusion in thicker materials. Use parameter control to manage added heat. Adjust travel speed, duty cycle, wobble diameter, and pulse settings to limit distortion while keeping bead width and penetration. The heat input does not govern the penetration depth. The wattage and the laser beam size does. The smaller the laser beam is, the deeper is the penetration. Deeper penetration and thin sheet capability. Dual-axis control enables both deep penetration welds and precise thin sheet welding down to 0.01 millimeters without damaging surrounding material. This makes them suitable for applications ranging from automotive frames to delicate electronics. Larger stationary units can achieve penetration up to 20 millimeters in a single pass, depending on laser power. Portable high wattage units typically reach about 12 millimeters, close to 0.5 inches, when operating in the 25 micron range. Laser welders are not a magic tool. Laser welding requires proper setup, calibration, and an understanding of material properties. Basic metallurgy knowledge helps because a laser welder does not replace the "I don't know" part, it only replaces the "how to" part. You can learn the mechanics of laser welding in 10 to 15 minutes, but understanding material behavior takes much longer. It is not just point and shoot. Misuse leads to weak welds, cracks, or distortion. The gun design expects the handle to be roughly parallel to the workpiece. In that position, the gun tube and the laser beam are at about 60 degrees to the material. If you run the gun too shallow, the beam bounces off the material, resulting in poor penetration or no fusion at all. If you run it too steep, closer to 90 degrees, the beam reflects back into the gun. The laser ray can cut through the dust lens, then the focus lens, and in some cases all the way back to the galvo mirror, destroying the galvo. If you are lucky, you only ruin 2 lenses, but some overseas units have 3. Material compatibility matters. Different alloys absorb laser energy differently. Some reflect more than others, with aluminum and stainless steel having the highest reflectivity, especially polished sheets or plates. In these metals, penetration is less compared to the same thickness of regular steel. Stainless steel, aluminum, copper, and titanium all require specific parameters. Titanium requires float welding in order to avoid contamination. Beginners often ignore this and assume one setting works for all, which is a mistake. Safety interlocks exist for a reason. Modifying interlock wiring or bypassing safety features can make the gun unsafe, even if they feel inconvenient. I began my video by explaining that I modified the safety lock for more than one reason. The main reason was pogo connector failure, and that problem is eliminated. But the other important part is float welding. Since my gun tube no longer needs contact with the part, I can run intricate welds by manually focusing the laser beam to achieve what I need. I only use this for decorative purposes because we fabricate a lot of architectural design products. In my field, float welding is a non-negotiable function. At the same time, if I had a new worker, I would never hand them my gun to run welds. A single misstep could have devastating effects. For example, if a cordless power tool is left nearby, the escaping laser beam could penetrate the battery casing. Lithium-ion batteries react violently to that, and I do not need to explain further. So if you do what I did, make sure you use it wisely. One major disadvantage of using a laser welding system is that you often have to elevate your parts from the welding table. How high depends on the type of laser unit you own. Some units have more flexible cable attachments to the gun, allowing you to run vertical weld beads closer to the table. But here is the issue. If your tube is locked onto the table and you need to weld vertically in a corner, you will have to deviate from the 60-degree angle. The gun geometry does not allow the handle to stay parallel to the weld profile. That weld will be defective, with a large amount of reflection, and the problems continue from there. The solution is to elevate the part as high as possible, or ensure that under your vertical weld profiles you have enough clearance for the cables to hang freely. You may not fully understand this now, but once you start using laser welding in your shop with parts locked into a jig table, you will see the problem immediately. At that point, you will realize you have to relearn how to jig for laser welding. That is the bottom line. Almost nobody is talking about that problem. Most of the flashy demo videos focus on "look how clean the weld is" or "this is faster than all other welding procedures," but they skip the geometry and jigging reality. The truth is, once your parts are locked down on a jig table, the gun's cable routing and angle constraints become the limiting factor. If you cannot maintain the 60-degree beam geometry because the table blocks your clearance, you end up with reflection, defective welds, or worse, damage to the optics. Elevating parts or redesigning jigs for laser welding is not optional. It is a fundamental shift in how you set up work. Laser welding is not just about swapping a torch for a beam. It forces a rethink of fixturing and jig design. Most first-time users do not realize this until they hit the wall in their own shop. I watched laser welding videos from well-known professional welders and YouTubers, and they misrepresented laser welding right from the start. If you think, "Oh, I know how to weld, so laser welding will be easy for me," you are mistaken. You may be
I
far
know what
ahead of a
I'm doing.
novice, since I assume you already understand metallurgy and material properties. But you are only just beginning to learn laser gun geometry and the problems it will cause with your regular jig setup. The laser beam does not care about your Siegmann welding table coating. It will burn through it like butter. And if you have a powerful unit, it might shoot straight through, leaving you with a Siegmann sieve. If you have any questions, drop a line in the comment section and I'll do my best to answer them. If needed, I'll make a follow-up video to cover your points in more detail. I also have a few additional modifications that I didn't discuss in this video, so make sure to subscribe and follow along. You won't want to miss what's coming next. Thanks for watching. I hope to see you soon in the next video.